Yes.
We have to be a bit careful.
Yeah.
Okay. I would like to welcome everybody for this one talk with number, what's the number of here, 12 or 13, possibly more than that, by Aamir. Aamir is currently a postdoc at Chalmers University. Before that, he was in ICFO, Spain. And before that, he was in ISC doing his PhD. He's going to be giving a talk on engineering symmetry-selective coupling of superconducting artificial molecule to microwave waveguides. It's an in thing, it's on quantum technology, so it's really exciting. To give you a very brief CV of Aamir, I don't need to see any paper because he was in our group. Did wonderful work on graphene and looking at certain aspects of quantum transport. Then he went to ICFO, worked with Dimitri Efitov on very interesting work on heat and specific heats in low-dimensional systems like graphene, and now he's working on this project. I'll not take much time, but there are things about Aamir that many of you probably do not know. When he joined his PhD, he was just 15 years old. So by the time he finished, he was just 21, 22 maybe. So I always believe that people grow academically after they finish their PhD. They're postdoc, they become professional. In case of Aamir, it's not even not just a professional growth, but when I saw him now, I think he's grown taller by about a centimeter or so. So, Aamir, all yours.
Which name to be used?
Welcome to my talk, and thank you, Arindamda, for the kind introduction. And I would like to thank Arindamda and Srividya and Akshay Singh for organizing this talk. So it's really nice to be back at ISC, specifically this physics auditorium, where I have given many talks before. And some talks were really terrible in the beginning, but I have improved over time. Let's see how this talk will go, because this is also a challenging talk in which I would be introducing you to some quite advanced experiments with superconducting quantum circuits. And this is something I didn't really know how to do less than 2 years ago, because I entered this field back in August 2020, and I have never done this experiment before. So I would like to tell you a bit about where I come from. So Chalmers University of Technology. So this is in this Nordic country, Sweden. This Chalmers University of Technology is an old university, and it has this department of microtechnology and nanoscience, which hosts a very state-of-the-art nanofabrication facility. And over the last some 2 decades or more, they have established a very strong expertise in state-of-the-art research in superconducting quantum circuits, which includes all design, fabrication, as well as experiments. And to base more on this expertise, there was a huge influx of funding provided by a foundation, Wallenberg Foundation. It's called the Wallenberg Center for Quantum Technology, whose goal is to who have put about 100 million euros to develop a 100-qubit superconducting quantum computer in about 12 years. And also another aim is to establish a long-term expertise in both academia and industry in Sweden. So it's a very good place to be working on superconducting quantum circuits. And while this was happening, it has been hiring many people in the just last 2 or 3 years. So one of those has been the formation of this new lab called 22Q Lab, led by the principal investigator, Professor Simone Gasparinetti. It's something which started in August 2020, which is also when I joined. And we began really with actually literally painting the wall in an empty room, and then we installed a fridge and we got experiments going. And as of now, we have several research directions, all in full swing of experiments. So one of them is quantum thermodynamics, which is what I am pursuing. And although I won't be talking about it, but my experiment or the work I'll present today is a precursor to what I'm doing in quantum thermodynamics. But aside from that, there are other interesting topics which we are already doing experiments. So others are, for example, microwave metamaterials, distributed quantum computing, continuous variable quantum computing, gate universe about superconducting electronics, and as well as we actually in-house build and develop a lot of hardware and electronics for quantum technology. And we are always hiring a lot of students and postdocs. So if you are interested, you can just talk to me, or you can directly contact them on as well. But also, before I go into the talk, I would like to also acknowledge the co-authors who have contributed to this work. So most of them are all of them are actually in our own team. And the funding has been provided by the Wallenberg Foundation as well as Chalmers. So I'm going to talk about, as in this talk, about an artificial molecule which is coupled to microwave waveguides. There is some interesting symmetries involved, and I'll be showing about how we engineered some couplings to the specific symmetries. So here's the outline of the talk. So I'll be basically give a bit of introduction, and one of that is in the context of waveguide quantum electrodynamics, which will be the theme of this, work. A bit of introduction to superconducting quantum circuits, as well as a bit about atom-light interaction in waveguide QED, which is going to be important to understand this work. Now, the main feature about this work is the specific device architecture which we developed in this. And with the help of that, I can break it down into 3 different experiments that we did. All of them are advanced and interesting in their own right. But just to highlight the device architecture, we put them all together. And then I'll end with the conclusion. So, introduction. When we talk about quantum electrodynamics, I can break it down into 2 different paradigms. And one of them is cavity quantum electrodynamics. This is the one which is most usually discussed. And the other one is waveguide quantum electrodynamics, which is the foundation of what I am doing. So cavity quantum electrodynamics is where you want to increase the interaction between light and matter. And in order to do that, you confine the light inside a cavity. So what happens is the light is bouncing back and forth often enough that the interaction becomes strong. And also at the same time, this also acts as a very good filter to protect the qubit from dissipative environment. And this is why the coherence time sometimes reached, specifically in superconducting quantum circuits, is of the order of 10 microseconds. And these are many of the factors why this particular paradigm is the leading architecture for quantum information processing and quantum computation. On the other hand, waveguide QED, over here, we don't have light confined at a certain frequency. We have a continuum of different photonic modes in a waveguide, which is basically confined in 2D, but they are propagating freely in 1 dimensions. But you can still get strong interactions with the atoms. Now, as a result of this, they are directly coupled to a dissipative environment because qubit has a particular frequency and excitation, and it could easily lose the excitation into this continuum of modes, and that is why this is dissipated. And the typical energy relaxation time, the T1, would be something like 100 nanoseconds. So it's quite short. It's not really so suited for quantum information processing. But there are many interesting other applications, such as you could use this as a single photon source. So this emitter, this atom could emit that excitation as a single photon into this waveguide. You can use it for quantum communications and some very interesting microwave quantum optics. So I'll quickly give us a quick survey about some selected applications. This waveguide QED is something, although it's not the most mainstream research in quantum electrodynamics, but this has many interesting applications, and it has been picking up in many different experiments. So one of the early experiments was to show resonance fluorescence, where the light was so strongly interacting with atoms that they basically hybridized together to give something called rest modes, and that was an important work in microwave quantum optics. You could use these atoms as well as mirrors. This was also an important work. And you can even go to some new regimes where you can have the atom which are very much larger than the normal atoms that we are used to. You could use this, for example, as a tunable on-demand single photon source, which is an important application in quantum communications. We can reach now non-classical sources of light, again, another important milestone. And the last one which I would like to talk about is something called collective effects. And this is also, which is what I would be talking a bit about in my talk. So in collective effects, what could happen is that you could have 2 atoms which are not interacting with each other, but they are resonant with each other. And because of the waveguide, they basically are able to talk to each other and interact with them without having actually a direct interaction. And this leads to collective effects, where they basically form some bright state and dark state, which I will be talking a bit more about. So in collective effects, what you could have is that you can have multiple atoms coupled to the same waveguide, and this waveguide would be mediating that coupling. And this has been shown back in 1954 that when you have such atoms resonate with each other, they form these collective states where they are either forming this state which are radiating in phase or radiating out of phase. And when they're radiating in phase, it's a constructive interference. They're radiating very brightly. That is why they are called bright states. And when they are out of phase, they are dark states. And dark states are interesting because that means dark states do not interact much with the environment. And therefore, you can have decoherence-free subspace. That is, they are isolated from the environment. And therefore, they're good for quantum communication and memories. But at the same time, for the same reasons, they are also very challenging to detect or work with them or control them. So one important factor which plays a role in this is symmetry. So symmetry plays an important role in the formation of this bright and dark states. And in this work, or there are some of these works which have somehow found a way to basically control them, but it is still difficult to detect them. So in this work, we develop a novel device architecture where we try to take control of that symmetry in this kind of devices. So this is something I've been talking about in a very general sense. So this is can be realized in many different platforms. But now I want to focus more into superconducting quantum circuits where we are going to realize this. So this is a very typical architecture. This is a very typical device idea where we have basically a waveguide over here, which are with a cavity in the middle, and there is a transmon or an atom over here. So the reason we use this platform, one of them is that with superconductivity, we can drastically reduce energy losses in the system. And therefore, if you have any excitation or a mode, they don't decay away because there's no resistive decay of this modes.
Sorry, Aamir, can I have a question?
Yes.
So regarding your previous slide,
yeah.
So you're talking about a Dyke effect. So if I understand, the Dyke effect is essentially in atomic transitions where collectivity forms a very sharp lines.
Yes, yes. So when you have a very sharp line, that means that it is a dark state. So the line width is really small, and therefore they are long-lived. Whereas when they are constructively doing, it becomes very broad and they emit very rapidly. That is why they are the bright state. So yes, this is something which was done in quantum optics early on, but now we have done this also with microwave frequencies.
Is your goal to create a sort of realize Dyke effect with superconducting circuits? Is that?
Yes, yes, but it has been done. For example, these works, this has been done. But when you form the dark states, it's difficult to access them because they are quite isolated. As you say, they have a very sharp line width. Now, what we have done over here is that we basically have a coupling in which we access both the bright and the dark state in a sense. So in this platform, superconductivity helps a lot with the energy losses. And it is very easy to tailor these devices. So you can engineer these devices to make artificial atoms with very tailored energy spectra. And also another important advantage here is that you have a very large vacuum field. So you have a very large vacuum field and a very large dipole moment in this architecture. And as a result, you can engineer really strong like-matter interactions, which are very hard to get in natural systems with natural atoms and natural cavities. And with this, which is something important, we can have a very strong efficiency, a very large coupling efficiency between the waveguide and the atom, which exceeds about 99%. Now, the typical building blocks here are waveguides. So, for example, this one, a waveguide means that it will confine the light in 2 dimensions and allow it to propagate in one of those dimensions. And the reason this particular architecture works is when you look at the cross section, we see that the electromagnetic field is confined near the central conductor and the ground plane. Now, if we terminate this as it is done over here at these 2 ends, then these terminations act like mirrors. So basically, your electromagnetic modes get confined; they keep bouncing back and forth, forming the sine waves. And this is how you form a cavity in quantum circuits. One of the ways that we form it. The other one is this the artificial atom over here, which appears somewhat like this. So you have 2 bodies of conductor coupled, connected to each other with a dissection junction. And I will tell you a bit more about this artificial atom and how this is realized. So if you look at a typical LC quantum harmonic oscillator made with an inductor and a capacitor, we can write down its Hamiltonian in this form. So it has the N, which is the number of Cooper pairs, and phi, which is the superconducting phase, when we have this kind of an LC circuit made of superconductors. Now, because this is an harmonic oscillator, you can see its form. We form this equally spaced energy levels, and these are basically what its energy spectra looks like. Now, on the other hand, when we have a transmon, what we do is to replace this inductor with a Josephson junction, and this is basically an anharmonic inductor, and as a result, its Hamiltonian has a non-harmonic term. So this particular one, which used to be phi squared, has become cos phi. And if you now look at the corresponding energy spectra, so now we don't have exactly this kind of a parabolic shape, but we have this anharmonic or nonlinear shape. And as a result, if we are in the right regime, where we can approximate cos phi to up to fourth order term, and in the limit that we have the Josephson energy, the part coming from the Josephson junction, larger than the charging energy, what we can have is again energy levels which are flat, like this, but they are no longer equally spaced. And in this case, the Hamiltonian appears like this. So it has this term which appears just as it appears for an oscillator, which is A dagger A after the second quantization, but also has this additional term which is called self-square term. This is the non-harmonic term, and what it means is that the higher levels do not have the same energy spacing. So in this case, the first energy level spacing is given by this expression. It's a function of the charging energy and the Josephson energy. And the second spacing, where the second energy difference over here is differing this by a negative component alpha, which is a non-linear anharmonic term, and that is also equal to the charging energy, the negative of that. So what now we have is because of this different energy levels, when we excite this transmon, this artificial atom, with this particular energy omega 01, and make sure that we don't have any component which is slightly different from that, we will only be exciting this transition and not this one. So as a result, we are confined only to these two energy levels. And that is what makes it the qubit, the two states which are accessed as long as you keep the same frequency, as long as you excite it with this particular frequency. So this is how we get a transmon to work or qubit to work. Now I'll show you what happens when we couple this qubit to a waveguide. So over here, I'm showing you in a circuit diagram. So a qubit would look like a Josephson junction in parallel with a capacitor, which has a Josephson energy and a capacitive energy, and then it couples to a waveguide via another capacitor with a coupling capacitance. So now I'd like to show you how we realize this in a fabricated device. So this is a schematic of that. So here the two pads form the two pads of this capacitor, and joining them with the Josephson junction, we basically have introduced this parallel arc of the Josephson junction. So this is the complete transmon. And now in order to couple this to a waveguide, which looks like a coplanar waveguide, we would have another coupling pad close to it, which basically mediates the capacitance. And now when we have this particular coupling, we can look at what is the coupling rate. So if there is an excitation, at what rate is it radiated into this? So that would be called gamma R. It's a coupling rate between these. So the Hamiltonian now would look something like, for the transmon as I showed earlier, it has this term. So the harmonic term and the anharmonic term. And now we can use this waveguide also to drive a transmon. Basically, we send a excitation, and that excitation will drive the excitation, the transmon between 0 and 1 state. And in that case, that Hamiltonian would have this particular term, which is proportional to the drive frequency, gap omega. And that omega depends upon how much power we put in. So if we are driving with a large voltage, we would be driving very strongly and make that excite the Q transmon at a very fast rate. So the corresponding omega again given as before, but now we know how to calculate what is that gamma R, the coupling rate between these. So it's proportional to the square of the CC squared and also inversely proportional to C. This is also dependent upon the characteristic impedance, which typically is 50 ohms in our case. And the typical parameters over here, the frequency, the transition frequency is in the range of 4 to 8 gigahertz. The charging energy, which is the enharmonicity, how different is the second excited state from the first excited state, is in the range of 550 to 200 megahertz. And the coupling rate, typically, again, we can engineer that, and we can make it either quite small, 0.1 megahertz, all the way to up to 40 megahertz, the typical numbers we play around with. So now that I have explained, shown you some, oriented you how we have this transmon and how we usually design that, now I will come to the device architecture. So the device architecture looks like this. So in this case, we have two transmons, right? So two artificial atoms. So they have been highlighted over here in this pink and the other one in violet. And Josephson junction, which is supposed to be in parallel, is over here. So they are joined over here. It's really small. So Josephson junctions are typically about 200 by 200 nanometers squared. So we have to zoom in and take an SEM image, and that looks like this. So this is a Josephson junction with joining two different plates with an oxide in the middle. So now, because these two transmons are next to each other, they also interact. So that coupling, again, we write everything down in terms of rates. So that coupling rate is given by G between this. And as a result of this, because these two artificial atoms are interacting with each other, that is why we call this a molecule now. It's a diatomic molecule. And now we have this specific geometry of this waveguide. So as I showed you earlier, one waveguide connected to one transmon. But now we have this particular one waveguide connecting to each of the transmon in a new fashion. So over here, this one joins the one on the left for each transmon, whereas the waveguide comes to this patch, which are next to each other. And it will probably become clear why we do it like this. But now let's look at what happens because of this interaction, G, between these two transmons. So this is the energy level diagram. So earlier I showed you those discrete energy levels. So now because we have an hybridization, or we have two of them, so we combine these two wave function or states together. So we have 0, 0, 1, 0, 2, 0 as we keep on exciting one of those transmons. Now the other one, when you excite that one while keeping the other one ground, so you have other one going as 0, 1 and 1, 1, and so on. And this G, the coupling basically couples the states over here. So 1, 0 with 0, 1, and 2, 0 with 1, 1 and 0, 2. So as a result of this, what we have is that the coupling between these two leads to a splitting. All right, so that's A and S. And I call this A and S because they have a form like this. So this one is called antisymmetric because it takes up a hybridized form with the 0, 1 minus 1, 0. And the other one takes up 0, 1 plus 1, 0. So that is the symmetric one, and it's higher in energy. And the same thing keeps on happening for all higher energy levels. So this
I don't understand what you mean by 2, 0, 1, 1, and 0. I mean, what are those 2 and 0 corresponding to?
Yeah, so you can think about each transmon as having excitations, right? So you can have the 0 state, 1 state, 2 state.
Okay.
And in the same way,
principal quantum number.
Yes. Okay. Right. So basically, going back to that picture.
This is a question we ask in interviews. How many is giving?
Yeah.
1, 1, and 0, 2.
Yes. So here, this is basically that 0, 1, and 2. But what is different here is that the 2 is not equally spaced to 1 as 1 is to 0. Right. So, but you still have all of them. And now I have put one more next to it. And they are interacting. So now what happens is that these two energy levels hybridize. And they happen at all levels. Right. So as a result of that hybridization, now we have this particular new hybrid states. And we call them antisymmetric and symmetric based on the symmetry of their wave function. This happens all the way to up. And what is interesting is that we could look at this in a slightly different way. So if we look at the Hamiltonian of the combined system, so these are basically the Hamiltonian, the harmonic oscillator term for each transmon, and the self-Kerr term for each of them. What we notice is that if we exchange the atoms, so we exchange the indices 1 to 2, the Hamiltonian looks the same. So it's something similar to what we know about bosons and fermions. But now that this exchange operators exchange the atoms and the Hamiltonian is invariant, that is expressed with this commutator. And as a result, all the eigenstates of the Hamiltonian will also be the eigenstate of that exchange operator. And the exchange operator can have either +1 or -1 when you exchange it. And that is why all the states that we get have this symmetry. So it's either antisymmetric or symmetric. So antisymmetric, I label them as red, and the symmetric ones, I label them as blue. So we have that all the way up. And this is again something fundamental because of the structure of the Hamiltonian. So there are these two different ways of looking at it. So now we have, this is the energy spectra, a spectrum of the diatomic molecule. And now we are trying to couple this to waveguides through which we will basically see any emission, or we will try to drive it by sending some microwave coherent light. So now for this, when we look at what this drive Hamiltonian looks like, it turns out that these two, so you will have these two different kind of oscillations. You can think about this like two coupled pendulums. So they are either moving in phase or they are moving out of phase, and these are the normal modes. In the same way, when we have oscillation in these two atoms, so you will have either these or two moving in phase, and in the other case, you will have this and this moving in phase. And in order to take advantage of this phase coherence, or basically this phase locking between these, we basically couple these two waveguides in this manner. So this one moving and couples to the antisymmetric mode. This is why we call this the waveguide A, and this one couples to the symmetric mode. That is why we call it waveguide S. And as a result, the corresponding drive Hamiltonians are given in terms of those particular annihilation and creation operators. So what it means is that this particular waveguide A is basically interacting only with the state A, or the transition going from the ground state to the state A, whereas the waveguide S is driving the transition from ground state to the symmetric state. But this does not end over here. What happens really actually is that these waveguides are driving certain transitions, and they are driving transitions going from one symmetry type to another symmetry type. So the ground state is the symmetric type, and this is antisymmetric. So this transition is driven by the antisymmetric waveguide. That is why I show the red arrow over here, whereas this transition is with the blue arrow. But when you go from the antisymmetric to the symmetric, or rather, sorry, symmetric to antisymmetric, you're changing that symmetry. And in order to change that symmetry, you need the antisymmetric waveguide. On the other hand, when you're going from antisymmetric to antisymmetric, you're not changing the symmetry, and that can only be driven by the symmetric waveguide. So in the sense, this waveguide are coupled to this specific symmetry transition based on the symmetry of the states. So typically, most of the time we are working with a few of these energy levels with one waveguide. But in this manner, what we have with these two waveguides is that we have engineered them to couple specifically to certain symmetries in that molecule.
These are.
Sorry?
All these are what you are talking like this with either solution. What is the measurement you do?
Oh, I haven't come to the measurements yet. That's comes next. So I'm trying to explain the device architecture, about why we designed this device in this manner. And of course, the next thing to do is to see whether this device does operate in this manner. So that's
what. I know that this is what exactly coupling is happening.
Yes. So this is the scheme, and now I'll show you the measurements, experiments. So the way we go about this is trying to measure.
One question in the chat box related to this previous slide. So the question from Saurabh is why the coupling between different levels of transmon follow a particular sequence.
Coupling between different sequence follow a certain sequence.
Why the coupling between the different levels of transmon follow a particular sequence like G and so on.
Oh, okay. Yeah. So this is something to do with the structure, with the harmonicity which we have introduced in the transmon. It is something we call. I'm forgetting the term used for this, but this is well known how transmon behaves. When we go to higher and higher levels, the coupling strength keeps on increasing with the number of the energy levels. So basically, when you go to the next one, it will be square root 3, and when you go to the next one, it will be square root of 4. So it has to do with the fact that when you do annihilation or creation operation, you pick up a factor, square root of n, and that has to do with quantum oscillators. So that's just that's something to do with that.
I add the reception to make it short.
Yes.
Make it unharmonic. Is there a measurement which shows that the energy level you can measure and show that they are actually level spacing are different? Is that what you can also demonstrate?
Yes, we can. We typically do that. Definitely, we definitely do that. But I have not shown that measurement in this talk. Yeah, but this is one of those basic characterization. Of course, when you have a transmon, we do make sure that it's really a transmon. It's really a two-level system, and so on. And there's a whole set of characterization. Sorry?
Make it harmonic with the reception. Why is it called transmon? Any specific reason?
Historic reason, really. So it's basically, it began with a transmission line oscillator. So they cut off a transmission line, and that basically why the transmission line became trans. and it became into that more. I forgot why it was more. Yeah, so it was plasma, right? So it was transmission line plasmon, and they fused that together to become transmon. But it's just a catchword, yeah. And there are very weird stuff, like there's Xmon and so on.
See, really it is an harmonic now because once you introduce the level specific become non-uniform. Is that something that we directly measure from this experiment?
Yes.
What is the
Normally spectroscopy. So you do reflections, you spend a tone, look at back what comes, and I'll show you some part of that, but I won't be showing really how we typically characterize the qubits. Yeah. Yeah, so the way we do it is basically we connect it to the waveguides eventually. So we have, and we use a vector network analyzer which has its own ports. And what it does is that it sends in some coherent microwave tones, just a continuous wave, and looks what comes back, for example. And then it will measure the ratio between those voltage output to voltage input. Now, as I go along, I will try to slowly introduce some terminologies that we use of quantum mechanics while doing these experiments. So one of them is the fact that when we use classical fields, when we are sending a tone, which does not have anything quantum associated with it, we usually we understand them as a coherent Gaussian states, which is a superposition of Fock states. If you were to look at a classical light and ask how will you represent that in the quantum language in terms of the Fock states, it will be a superposition of many Fock states. And one specific feature of this is that they are all eigenstates of the annihilation operator, which means that when we try to, so if you take out one photon out of this wave, out of this particular classical light, it still looks the same. And that is how we understand classical continuous wave here. So when we do this voltage measurement, they are actually a measurement of A, because the voltage operator is given as A plus A dagger in the second quantization language. And that is why when we want to measure V out by Vn, is essentially measuring the steady state or the expectation value of the annihilation operator. And those particular modes which are leaving the vector network analyzer in ratio with the one which are coming back. So basically, this is how we sort of connect what we measure in the instrument with actually the operators which are basically involved when we are doing these measurements. So when we look at this classical tone, the average number of photons given in the classical fields is actually mod square of this eigenvalue. And the power of this coherent tone is given, multiply this particular number of photons with the energy of a single photon. So that's h cross omega. These are the measurements we will be doing to understand our device. And now I'll also tell you a bit about the experimental setup. So our device is somewhere sitting at about 9 millikelvin in the dilution refrigerator. And we have a way of doing reflection spectroscopy where we want to send in a tone into the device, and it goes and hits the transmon or the device, and then it reflects back. So when it reflects back, we want it to go to another channel where we will have an amplifier to measure the output. And in order to do that, we have this microwave circulator. So what it does, it's a non-reciprocal device. It will route any signal going into the device, but all the outgoing goes through a different channel where it is then amplified. And we also use a few attenuators at different stages, because at each stage there is some thermal noise in the form of electromagnetic modes. And those electromagnetic modes are also traveling into the device, and they could excite a transmon. We don't want that. In order to avoid that, we put these attenuators, which basically just reduces the power of all this noise down to a very low value such that they do not affect the transmon device. And since they are really high, we also have to apply enough power so that they can overcome the attenuation along these lines. Now, in the fridge, it looks something like this. So this is the dilution fridge, picture of my fridge. So we put the device somewhere here, which is at about 9 millikelvin with all these wires, goes through all this various different stages until all the way to room temperature, where we have a vector network analyzer to measure this. So now I will come to the symmetry selectivity, the reflection measurement, which shows the coupling which I talked about. So what we do have is this kind of, we want to make sure that when we send in some continuous wave through this waveguide, we are only driving this particular symmetry, this particular transition of this symmetry, whereas with this one, we are driving this particular transition. What could happen is that we might be driving this also with this, or this with that. That is what we want to check, really, whether that works or not. And so this is how we will be basically doing the measurement. We'll send a tone and look at what reflects back. Now, this kind of measurements are really elaborate, and I could spend a lot of time trying to explain this. So I will try to keep it simple. So what we do over here, so this is the result of reflection spectroscopy, where we are looking at the reflection coming out at this particular frequency, which is about 5.698 gigahertz here. And this is what we identify as the symmetric mode, anti-symmetric mode. Whereas when we go to a high frequency where we expect the symmetric mode, we don't see that. But if we zoom in, we see a small dip. And I'll say what that is. And vice versa, when we go look at this from the other waveguide, we will see this particular mode where we saw the small dip, but we see a strong dip over here. And on the other hand, when we go back and look at this is a very small dip. So what's happening? And typically, we actually model this data quite accurately. And the way we do it is, what we want to measure is the reflection coefficient. So again, it's given in terms of the voltage we measure output to input. And we apply something called input-output theory in order to understand what's happening. So we are sending in some tone, which is A input. All right, so this is represented by that annihilation operator. And this gets then reflected back and gets scattered by this mode, so that looks at A output. And what we now know, if you look, so this theory is it's just basically like a Kirchhoff's law. What goes in will get scattered back, as well as some contribution coming from that particular state, which is decaying. So when it decays, you will see that this will have a larger value, and you will have some contribution to what is coming out. So we can solve this with something called a master equation. Again, I'm not putting all the equations here, but after solving this, we come to an expression for what the reflection should look like, and that depends upon these various gammas. Again, this gamma is basically the coupling rate of this particular transition with this, as well as this particular coupling rate to something else, and it would be this. So what we find when we do it at this particular specific powers, we see a strong dip, and it allows us to fit and extract these gammas. So there's gamma over here, gamma A turns out to be 0.311. And the one which is going out to the other waveguide turns out to be 8.8 kilohertz. So it's much smaller than that. And in the same way, when we find out what is this particular gamma while trying to fit this particular dip, we find that to be 1.388 megahertz. And it is much smaller than the other gamma S after the fitting, which is about 29.8 kilohertz. So what happens is that, so what it means is that this particular state, as you said correctly, as I said, it couples to this, but it also couples slightly to this. So it's not perfect as we would have liked it to be. And that is typically quite common in these kind of devices. You can engineer it all you want, but at some point you have a little bit of cross couplings. But what we try to do is to minimize the cross coupling, that it is negligible. But in this measurement, we can actually measure that or actually fit that and find out this ones. And if we look at the ratios about how much of this coupling is larger than this one, that turns out to be gamma A by gamma A prime to be 35. So it's much more than a factor of 10. And the same is true with the other transition.
You're basically looking at the selectivity.
Exactly. So this is the selectivity about really how selective is this particular waveguide while driving this transition, or vice versa, how selective is this one coupling to this one. And that's exactly the selectivity. But the whole point is that how selective can we make to that symmetry? Exactly. And with this fits, we were able to see that these factors are really large enough that we can do some other interesting experiments based on this. So this is basically the part which was the first experiment, a set of experiments to establish the selectivity of symmetry. Now I will come to the second experiment, which is sort of an application. Yes? So when I'm doing experiment, it's only one is active. So I'm looking at what goes in and what comes out, right? But what I know is that if I push enough power, so there's a very weak coupling. If I push enough power, I can also do transmission measurements. I can see how much is coming out of here, and I've done those measurements just to verify roughly that my parameters were correct. Oh yes, so yeah, so we have one more pair on the other end also, which I sort of omitted here. But we exactly, so this is just a king to just show. Yes, so when you see a dip, you know that you're basically hitting a transition. Yeah, I'm not touching it. Yeah, I'm not touching it when doing that experiment. Yeah, so
when you say that reflection measurement, the symmetry versus anti-symmetry combination.
you mean look at which wave function it is?
Is that possible?
No, so we haven't done that
Well,
experiment.
essentially, the energy scale at which your resonance is happening will depend upon the symmetry and symmetry.
So everything needs to be anti-symmetric only with omega gamma value or the frequency. Is that the way you are detecting? Or how do you claim that this is the anti-symmetric part of the combination?
Yeah, so it's based on basically. So we have simulated this also. We have done this calculation in a simulation where we basically plug in this particular Hamiltonian and calculate what are the transition rates when you excite from one waveguide to the other waveguide, and that basically completely is basically what we find also in the experiments.
We have this. You see the D that probably is what you get from the simulation. That's the way you detect.
Yes.
So you can answer the question is to be yes, no? That you can identify the resonance.
No, I thought you were asking whether I can find out that when I find a transition, it's really this wave function or not. And what we are measuring are like energy. We're not really measuring the wave function. Although I will show my third experiment sort of will shed light on that. So it will sort of, again, we will do an experiment which will ascertain this particular level diagram. But again, it's not super direct. It's not absolutely direct, but it's in another way.
You can be absolutely predictable. You know the pole which is coupled to anti-symmetry, and then the pole which you coupled to symmetry. So whether you are using S11 or S22, a perspective will know anti-symmetry.
Oh yes. That is clear. I thought the question. Okay, maybe I didn't understand the question. Okay, I thought what you wanted to say whether if I find this energy spectrum, how do I know what is its wave function? And that is something. Okay. Yeah, but basically we also simulate all of this. So we, the good thing about this is that we put this through our simulation software, and we get all the. Let me just show you the parameters. Yeah. So I calculated this from simulation and calculations, and I could get the values of G, gamma, A, gamma, S, gamma, all of these gammas roughly to a ballpark value before I did the experiment. And this is because we engineered it in this manner. And on top of that, this omega A and omega S also fell very close to what we expected. There's a bit of uncertainty in the fabrication where the reception junction could be slightly different from one fab to another fab. So because of that, we couldn't exactly predict it, but it was still close to what we expected. Yes.
So is it possible to do this like mainly the ratio of the two components? Is it possible to increase it by changing either the reception junction or the waveguide?
Yes. So this gamma, as I showed earlier. Right. So this gamma is given by this this expression over here. This expression over here. And while designing the device, I was tuning this CC as well as C and also omegas. There's a bit of uncertainty what will be omega again because of the reception junction, but pretty much it can be tailored to whatever I would like it to be. So again, it was something tailored around to be about 1 megahertz, and we got the numbers around that.
Maybe we can have the questions later because we can finish.
Oh.
I mean, we've got 10 more minutes.
Oh, okay. All right, so the other experiment that we do is coupling between states of opposite symmetry. So I showed that we have these two different states and they are really isolated to each other because they're like normal modes after the hybridization. But via a higher level, we can couple them to each other. So we can, if we have some excitation over here, we can transfer it to the other one. And in order to do that, we use this Raman process via this virtual state. So in order to do this, we basically have to tune the coupling strength between them, given by how much pump amplitude we apply on both these transitions. So this is basically like a frequency converter. So we are going from one particular frequency of anti-symmetric mode to that of the symmetric mode. And this is via this particular intermediate levels. And with this particular scheme, we have been able to do a coherent population transfer, which means that if we start with this particular state completely filled, we were able to transfer all of that up to 95% into the other one. And this data basically shows that when we apply this pump, so when we keep on increasing this pump, in the beginning we don't see any transfer, but after sufficient pump we see some transfer, and then it basically keeps on decreasing a little bit. To show us a cut over there, so this is what it looks like. The transmission going from here, actually in this case I'm going from symmetric mode to the anti-symmetric mode. So we have a strong peak when we are at the optimal pump power while we are driving this optimally. And in this case, we see a peak which almost reaches 0.952%. So that's 95.2% efficiency. And in the other case, when we apply, correspondingly, we see the reflection also zero, which means that whatever we are sending in is actually going through. And on the other hand, when we do this as a function of the pump amplitude, we again see that there is an optimal omega at which this is maximal, but above and below it, it will decay off. And again, this is something we can model with a very basic Raman model. It's just a 2x2 Hamiltonian, and with that we were able to fit this data quite well up to this point. So this is the second experiment. What we wanted to show is that although we have two different symmetries, we can still couple them. Now I will move to a third experiment, but before that I will have to introduce this new circuit where we will be applying pulses. And this is the full circuit, which might look a bit complicated, but I can summarize this basically over here. So what we do is send pulses which are very short. So here we can send pulses. So instead of sending a continuous wave, we are sending pulses which are about 10 nanoseconds to about 10 microseconds long with a carrier frequency. So inside this pulses, there's still a carrier frequency of 4 to 8, supposed to be the same as the qubit frequency in order to drive that transition. We acquire the voltage. So when we send this into this, it gets scattered by the qubits or by the transmon. And again, it is rerouted via the circulator, and then we amplify and detect it. But now again, this is happening at a high frequency. So we'll have to use mixers to down convert it. And then we basically acquire these measurements in a span of a few microseconds. And these pulses are really very short. So the signal to noise ratio is really poor. So in order to achieve enough SNR, we have to take a lot of averages of the order of 10,000 to 10 millions in order to improve this. So now I will go a bit more into what that pulse sequence is. So here, this is basically that particular diagram again. So we have, we can start with the ground state, but when we send in a pulse, what we do is we drive this transition. And driving this transition in the block sphere, so if we just consider these two levels, like a two-level system, we can describe that in the block sphere. So there's the ground state, and there's the state A. And by applying sufficiently strong pulse, what we are doing is basically rotating this. Now we don't do this continuous wave, because if you're doing continuous wave, it will keep on rotating. But now we want to, for example, rotate from ground state to the first excited state. So we need to apply that continuous wave for a short time. And that short time could be typically of the order of nanoseconds. And depending upon the duration of that, that will tell you how much it will rotate. So by that rotation is given by this theta. So when we apply something like, for example, a pi pulse, we call this pi, it means that I have rotated from ground state to the state A. That's exciting that state. But this will keep on rotating the longer I put or the more amplitude I put over here. And again, whatever I am putting in, we can characterize that in terms of the operator A, the annihilation operator. And then what comes out is the A again, but that is the output one. And so the theta is actually proportional to the height and the time. So you can again increase the theta either by increasing the height or by increasing the duration, because during that time it will keep on moving. So when we do this, so here's again a quantum state where now I'm showing you the zero of this particular state of the molecule. And the second one is the state which is basically in this one, inside this line. So we begin with something, let's say ground state, and there's nothing over here inside the output line. Then we send in this pulse. So we have applied basically a Rabi angle and rotated this by a theta. And in that case, the first one basically looks like this. It's basically a cos theta by 2 plus I by sin theta over here. Now what happens is that once we have driven this, it will again decay back into the waveguide, which means that whatever we had, whatever scope of excitation we had over here will decay back into the waveguide. And now that appears again as a superposition of the Fock state 0 or the Fock state 1 photon in the waveguide. So that particular angle basically got transferred into the microwave mode, which is propagating away. So in order to see that propagation, we again measured on this end, the output line. And as I told you earlier, we acquired it over a few microseconds. So this whatever is being emitted appears as a voltage signal, which is decaying with time. And this decay again is dependent upon the coupling rate, which we discussed just 2 slides ago. So the coupling rate, which was about 0.31 kilohertz or 1 megahertz, is basically at what rate this voltage, this excitation is decaying into this, and I'm measuring that in a voltage signal. So this is that data. This is the data where what I've done is applied a theta, which is pi by 2. So brought it all the way to the state A, and now it will decay back into the ground state over time. And that decay rate is given by 2 by gamma, the gamma we found, which is about 930 microseconds. And that is something we measured. Again, this is a signal which is really weak. This has been averaged, this trace has been averaged about 200,000 times. So this is how we basically, we can look at emissions of excitation from the molecules.
The X is there. The unit is microsecond, but then I see it gamma is in 930 microsecond. 1 volt would be maximum.
I'm sorry, this is the typo. This is nanoseconds. Yeah, sorry about that.
That makes a big difference.
Yeah. It's supposed to be very weakly, strongly coupled, so it decays away fast. All right, so now what we could do is also look at Rabi oscillation. So what we do is basically we'll give it a kick and we see how much comes back. So this particular amplitude, it depends upon how much kick we gave, how much theta we applied. So when we give it all the way up to this particular the state A, if we go up to this point, we see, so at this point actually we see a dip when we are maximum. So this is basically a pi pulse. So this is how we calibrate our pulses. So when we see a dip particularly over here, we know that we have applied a pi pulse. This has gone all the way over here. And when we apply over here, it keeps on rotating. So that is why we see this oscillation.
What's the y-axis? What's the measurement?
It's just a voltage measurement. Yes. Voltage measure. So actually, no, sorry. This is basically, we get this particular trace and we integrate under this. So that's the voltage, proportional to voltage. Okay, so here it gets a bit technical, but what I would try to say is that what we are trying to do now is calculating moments and statistics, which means that, again, this is something which we get, we can send one pulse and get a measurement out. We can keep on sending this and get those measurements out, and these are called single shot measurements, and we keep on recording them. And then we take statistics, we can take average, we can see cross correlations, and this is important for the next experiment. In order to capture this, we do something called temporal mode matching, and it's something technical, but the matter is basically we are basically trying to find what is the moments of this annihilation operator and its statistics. And we know that given a particular Rabi angle, we would get moments which we can actually calculate. So we know this is what our wave function looks like. And we calculate the expectation value of A, which is what we measure with the voltage. So if you calculate the expectation value with this, we will find it goes as e power I phi sine theta. And we calculate the expectation value of the number operator. So A dagger A is the number operator. How much photon you have, that goes as sine theta by 2 squared. And it makes sense. So when we apply a Rabi angle which is 0, this one is supposed to be 0 because there is no excitation over there. When we apply pi, then we have gone all the way to the state A. So there's one excitation. And that means we will see a maximum that appears as one single photon. Okay. So basically this is how we calculate these moments. And this is important in this experiment where what we have a pulse sequence where we send a pi by 2 pulse and make a superposition state between these two levels, ground state and A. And then we send a theta pulse where we take whatever is remaining into the state S. And now whatever we had, so when we send these pulses, we had a coherent. So what we end up with is a superposition of these two states, which is like an entanglement. And the final state appears like this, which is, this is where what happens after we apply the theta pulse. And then whatever entanglement we had over here, they decay away into the waveguides. So that entanglement gets transferred into propagating photons. So this is basically what we have over here. And if we go to the limit case where theta is pi, what we have is a Bell state. And this is something very important for quantum communication. And this particular Bell state, if you again take the expectation values of these parameters, you will see that the moment of the single annihilation operator is 0, but the cross correlation gives you 0.5. And this is the important number which will tell you whether the propagating modes are entangled or not. So we did this experiment where we basically did this as a function of this particular theta, and the experiment we find they are actually matching very well what we would get if you just take the expectation value of these parameters on these states. And what is important is that when we look at the cross correlation at pi, where we expect the Bell state, we do see about 0.5 in both cases, which is, and in the case when we don't apply this particular pi by 2 pulse, we don't have an entanglement. We don't see this cross correlation. So this is the evidence that we have a Bell state in propagating modes. Again, this is something which has been done in other ways, but this is one of the most simplest ways of getting entanglement in propagating modes. So that's the third experiment. So I will now conclude. I introduced a device architecture. We showed an experiment to show a very symmetry-based coupling. A second experiment, we could show a coupling with between opposite symmetries with a Raman process. And the third one is the application of entangled modes, entangled itinerant microwave fields into different waveguides. And this has many more applications we could think, but we stopped here. But the reason I was doing this was to develop this particular device for quantum thermodynamics. So that's the new generation of device which I'm about to measure soon. But we have put this also already in archive, and it's right now under review in PRL, where we have got good reviews. So you could find also in the preprint on archive. Thank you.
All right. Questions? Yeah.
What kind of transitions are the AMS are the coupled against it, right? And 0 and all are uncoupled against it.
So actually, none of them are. Just give me a second. So that the audience can see what I'm showing. Yeah, so all of these states are uncoupled to each other. So these are basically what happens after, these are all eigenstates, so they don't couple to each other. But by taking advantage of this Hamiltonian, the drive Hamiltonian.
You want to put in a presentation?
Is it visible in the, yeah?
You can make it bigger.
Oh, okay.
No.
The Fox states remain even when they're coupled.
The Fox states.
Sorry, 0 and 2 minus.
0, 2 minus. they are the states of this molecule. We don't call them Fock states because it's not a quantum harmonic oscillator. They are in the waveguide, so that's where we will use those terms. But conceptually, they are the same, I mean, fundamentally. And yes, they are eigenstates and they are uncoupled to each other. Unless you add in another Hamiltonian drive, which will allow you to drive the transition between them.
Next. Yeah.
There was this optimal power.
Experiment 2.
Yeah.
Yeah.
Optimal power.
Yeah. So it's a virtual process where you are driving a transition. You're driving the population. We call it a population, the excitation that we have, to the virtual state and then back into that state. If you populate on one end too much, then you're not able to get them on the other state and propagate away. If you do it too less, you're not transferring enough population. So there's an optimal point where it is the best. Is it frequency dependent on which one?
I can see the red curve. It is at the peak for that is the state I guess.
Oh yes, so yeah. We are transferring from.
Right now is transferring from the symmetry to entity.
Correct.
Right. So, and you are trying to say that when the rate is peak, what is you are trying to do? You are trying to put that optimal power. You are trying to put that much power to symmetry. So the symmetric to the anti-symmetric. I mean, it's a transmission measurement.
Correct.
You are putting this S4 and measuring at the airport.
Correct.
With the optimal power.
Yes.
I'm saying when this basic question, I'm saying I can see towards the start of the graph. Do everything. Is it the same optimal power you're reaching, or you have changed the optimal power?
So let's see. You're talking about. So you're talking about why this over here.
It is a rod.
I mean, I could say if we change the optimal power, maybe the red curve, the baseline will sink down.
I guess his question is, T depends at what
No,
factor?
the left side graph.
So is that
Yeah.
if the power is larger, will it increase?
Yeah, so this is done at the optimal power. If I didn't do this at the optimal power, this peak will be smaller. Okay. Okay.
All right. Next. Yeah.
There's actually a question
from chat box. Please go ahead.
So, Mala did try to answer. Which parameter controls the cross coupling between symmetric and anti-symmetric channels? Is it related to device?
Yeah. So designing this device has been quite challenging because it depends on them in a very. So I haven't shown it here, but it depends a lot on how the capacitance matrix is distributed. So here.
And Bala here.
Yeah. So what is happening here? So we have a strong. So you can break this down into a capacitance matrix, right? So you have a capacitance between this to the ground plane, between this, and there's a capacitance between this and this, right? So now this, although we try to make it symmetric, it's not so symmetric. I mean, inherently there is some asymmetry, and that is that the coupling between these two is strong. So when we look at from these two waveguides arms, with respect to that, we have a capacitance over here. But when we look at between this and this, in order for it to be the same, I should have a capacitance between this and this, which is same. However, they are far apart, so that capacitance is already low. So there's already some inherent asymmetry in this device, which is what is contributing to this different coupling rates to different wavelengths.
Just offset them slightly.
Yeah, I played around for days, moving them around until I got an idea and intuition about what I need to do. So basically what I had to make sure is that the capacitance between this and this is dominant over the capacitance between this, while also keeping them close enough so that I have enough splitting between them. Yes.
I have a question about the entangled state. So how they are coupling to the symmetric and asymmetric code? The coupling is same or it's different?
Oh no, so based on what we have over already. So once we have established that coupling, that their coupling is strong between this and this, we have that mode. But that is right, as I told you, it's a small coupling from here to here, and that happens. And that is not good for entanglement. Because for entanglement to be good, it has to go from here to here and not the other way around. And that is why we can calculate something called fidelity. It's one of the questions which I have to actually answer. So I'm calculating the entanglement fidelity to tell really how good, how ideal is this entanglement. But that is a problem, the cross coupling. And that is why it was important to make sure that that cross coupling is as minimal as possible. So we do see the entanglement as shown over here, but it's something, it's still not ideal. And that means that more engineering could be done. Although I think it's fine enough.
Any further question? I have this, no one, right? Okay. A short question. I mean, from a person who is, okay. So at the end of the day, you are playing with two atoms.
Yeah.
Doing physics, sort of, whether it's Dirac effect or some other effect. So can we think about what kind of interactions in solid state one can emulate with just two atoms that you could demonstrate using this two atom molecules. Mm-hmm. So, for example, okay, symmetric and unsymmetric is probably the most primitive one you can think about. Right?
Yeah.
Great. Can one go beyond this and say what else can one do?
Yeah. Yeah. It sometimes feels like the possibilities are endless in circuit QED. So I'll give you an example. Although this is not what happened in this experiment, but I did this in another project which I was doing with a PhD student. So over here, the coupling between them is capacitives, and that is why they hybridize. Now, what we often have is for a quantum computation architecture, we have a coupler between these. So that coupler is also doing capacitive coupling, and it kind of mediates it, but it's extremely weak. Now, what you could do is to drive that coupler. So you send in a tone at the frequency, which is the difference between the frequencies of these two. So that's 2G in this case. So you apply a tone which is moving at 2G, which is quite small, so it's about 600 megahertz. And when you increase that, you could increase the coupling between these two, which means now you have a tunable coupler. So you have a tunable coupler where you can play around between these two, increase the coupling by will. Okay. And again, this is some of those tools which you could put together and explore some interesting Hamiltonian of your choice. So you can tailor a lot of different Hamiltonians with 2 qubits itself. And it seems like you can tailor most of the interactions you could think about with just 2 atoms.
I mean, the kind of thing that you did is the first step towards tight binding model.
Yes.
So essentially, symmetric and asymmetric, you put many of them, you get a line.
Yes, absolutely. That is also done, yeah.
Tell me what can we do with two? What more Hamiltonian one can look at with just two of these atoms? That you can simulate. I mean, using your coupling change or tunability. I'm seeing from outside it's just 2 atoms. What can I do with these 2 atoms?
Well, I think there are applications. So one of the applications which I am thinking about right now to do with quantum thermodynamics is once we have this hybridization, we are trying to basically apply a dephasing element. So we have a squid over here, and next to it we put a flux line, and on the flux line we send noise. And by applying that noise, we are increasing the dephasing. And therefore, you could go, for example, from this pure states to a mixed state between these two. So you can tune interactions, you can dephase them. Okay. You can pretty much do whatever you would like to do. You could think
electron-electron interaction, simulate electron-electron interaction in a system like this. So I already have atomic orbitals. have electron-electron interaction? Do we use this?
With the coupler, yes. With the coupler I mentioned, you can increase the interactions, yes. And you can do things with coherence and phase as well. So I mean, for example, if you were to think about the Kane-Millet model where you have this imaginary coupling term, even that could be done with this kind of couplers. Yeah.
Okay. Now the question, I would like to thank Aamir first, but then there would be an announcement from Akshay, right?
From Arindam.
All right, fine. So that's fine. I don't know what the announcement is. So
Just that one talks this thing.
okay, one talk is very good, and we need better participation, and we would like to have one talks very regularly. I mean, and you know, this is something which brings about a large number of people from diverse background, and we would like strong student participation. We have started this in a hybrid mode now. This is the first one in hybrid mode, and I think what it does is something similar to what Aamir has told us today, right? Because we can connect technology with the basic solid state physics, chemistry, you know, to it. So I think if we can appreciate that, I'm hoping that it will become very popular among students, not just in this department or several other departments where the engineering and chemistry is happening. So I would like people to keep an eye out for quantum announcements. And I'm pretty sure there are a significant number of very exciting talks here. Is that okay?